Welcome in .Core. In our previous series, we explored the JWST black hole theory and the mysterious universe inside a black hole. Now, get ready for an even bolder idea, a mission to send a tiny probe straight to a black hole. Led by astrophysicist Cosmo Bambi, this plan uses powerful Earth-based lasers to launch a nanocraft to one-third the speed of light. If a black hole is within 20 to 25 light-years, the probe could reach it in 70 years with data taking another 20 years to get back. This game-changing mission will push the boundaries of our understanding of black holes and spacetime itself. Keep watching this video to dive deeper into this groundbreaking concept. The mission concept at the heart of the proposal is a nanocraft, a spacecraft weighing only a few grams built around a microchip and a thin light sail. Instead of rockets, it would be accelerated by a powerful beam of lasers from Earth. The pressure from this light would push the sail to around 100,000 kilometers per second, one-third the speed of light. At that velocity, a black hole 20 to 25 light-years away could be reached in about 70 years. The probe's data traveling at the speed of light would return to Earth in about 20 more years. The main scientific objectives are clear. Confirm the physical nature of black holes. Study how spacetime behaves in extreme gravity. Gather data to test core principles of physics in conditions impossible to replicate on Earth. The first hurdle is locating a nearby black hole. The closest confirmed one, Gaia BH1, lies more than 1,500 light-years away, far too distant. But astrophysicists suspect that smaller undetected black holes may be hiding closer to us. Observing the motion of nearby stars or detecting gravitational lensing effects could reveal one within range. The second hurdle is technology readiness. We don't yet have nanocraft that can survive decades in interstellar space, resist constant cosmic radiation, and send back meaningful data from so far away. The laser infrastructure needed today would cost roughly €1 trillion, though projected advances could reduce that dramatically within decades. This concept builds on ideas already explored in projects like Breakthrough Starshot, which aims to send similar nanocraft to Alpha Centauri. The black hole mission pushes those principles further, both in distance and in the precision needed to survive such a hazardous destination. Scientific value and potential discoveries: black holes are natural laboratories for testing the limits of physics. Their immense gravitational pull distorts spacetime to extremes, making them ideal for examining how the universe behaves at its most intense. One focus is the event horizon, the invisible boundary beyond which nothing escapes. If it exists exactly as predicted by general relativity, approaching it should reveal specific patterns in light, energy, and particle behavior. But some alternative theories propose different structures, such as a surface of exotic matter. A close probe could provide definitive evidence one way or the other. Another aim is to test Einstein's theory of general relativity under conditions far more extreme than those observed so far. While the theory has passed every test from planetary motion to gravitational wave detection, the intense curvature near a black hole could expose effects or deviations we've never seen. Other potential discoveries include direct measurement of gravitational redshift and time dilation near the horizon, insights into accretion flows and magnetic fields, detection of possible quantum-scale effects at the boundary. Beyond pure science, the mission could advance several critical technologies. Laser propulsion could make interstellar travel to nearby stars feasible in decades rather than millennia. Miniaturized deep space instruments would lower mission costs and expand possibilities for multiple probes. Radiation-resistant materials developed for the craft could be applied in satellites, space stations, and even terrestrial industries. Importantly, these spin-offs mean that the mission's value isn't tied solely to its completion. Even partial progress toward the goal could yield major technological and scientific gains, much like the decadecade-long efforts to detect gravitational waves or capture the first image of a black hole. Challenges, timelines, and future steps. The mission's biggest challenge is identifying a reachable black hole. Without one within 25 light-years, the concept remains theoretical. Upcoming astronomical surveys capable of tracking minute stellar motions and spotting gravitational lensing events may provide a target within the next decade. Engineering is the second major obstacle. The nanocraft must survive decades of exposure to cosmic radiation and micrometeoroids, maintain functional power systems without conventional fuel, carry instruments capable of collecting useful measurements within extreme gravitational environments, transmit data reliably over interstellar distances. The laser propulsion array is a separate challenge. Building a system powerful enough to accelerate a nanocraft to one-third the speed of light is unprecedented. At current technology levels, it would cost around €1 trillion. Bambi estimates that within 20 to 30 years, advances in energy generation, laser efficiency, and manufacturing could reduce this to roughly $1 billion, similar to the budgets of flagship space missions. A realistic path forward might include black hole detection, identify a suitable target through next-generation surveys, prototype missions, test nanocraft on shorter journeys such as to the outer solar system, incremental laser array construction. Start with smaller-scale propulsion tests before committing to full capacity. Interstellar demonstration, possibly to a nearby star system before attempting the black hole mission. This is a long-term project by design. The scientists who initiate it will not see its completion. Instead, it would be a generational effort requiring sustained commitment over many decades. History shows persistence pays off. Gravitational wave predicted in 1916 were detected in 2015, and it took over 50 years to capture the first black hole image in 2019. If successful, this mission will be the first direct exploration of a black hole with the technologies developed reshaping interstellar exploration for future generations. Outro sending a paperclip-sized probe to a black hole may seem like fiction, but it's grounded in active research. This mission could reveal new physics by exploring spacetime and gravity at their extremes. The challenges are immense, but history shows that persistence can make the impossible possible. Even if the mission doesn't launch soon, the pursuit itself could drive advances in interstellar travel and deepen our cosmic understanding. Stay tuned as we explore how these bold ideas might shape. Thanks for watching. Cool.